Welcome to General Chemistry Mini Lecture Series, Lecture 33, The Particle Nature of Electromagnetic Radiation. First, let's go over the photoelectric effect. When light hit on the surface of a material, for example, metals, electrons are emitted. This phenomenon is called photoelectric effect. According to a classical electromagnetic theory, the photoelectric effect is caused by the light energy being transferred to electron. Also, if the wavelength of the light is made shorter, the light wave's intensity made brighter, the more electrons should be knocked out. However, this theory is not supported by experimental results. Scientists observed that there was a threshold frequency for electrons to be emitted. Below that threshold, no electrons are emitted from the material. Doesn't matter whether the light intensity is higher or lower, or the length of the exposure time is longer or shorter. Scientists also observed that above that threshold frequency, light with a dimmer source still cause electron emission. Electrons are still knocked out using dimmer light and without any lagging time. So we need better theories. Later on, Einstein proposed that light energy is delivered to the atoms in packets called photons. The energy of photons is directly proportional to the frequency of the radiation, and of course inversely proportional to wavelength. And that proportionality is a constant. We call that constant Planck's constant. It carries a value of this much. The unit is joules second. Okay, this is the key equation for the particle nature of light. Energy is directly proportional to frequency, but inversely proportional to wavelength. The higher the frequency, the higher the energy. The shorter the wavelength, the higher the energy. We now work on example number 1 in this lecture. This is the frequency of a microwave. So let's label that first, frequency. And we need to find out the energy of one photon of this microwave radiation. So, and this H is Planck constant. We already know frequency. We already know the Planck constant. Frequency, Planck constant, Planck constant. So therefore, we can easily calculate E, the energy. Just plug in those numbers and make sure you use the correct units. Bingo, it's done. This is the answer for the energy carried by one photon. Let's work on the second example. What is the energy of 1 mole of photons of radiation with a wavelength of 500 nanometers? So again, let's identify those known information. 500 nanometers is the wavelength, is the Planck constant. Again, the energy for one photon can be calculated using E equals h nu. We don't know nu directly, but we can rewrite this equation to H times C over lambda. Now we know lambda. And of course, we know C. It's a constant, should be always given. Planck's constant times speed of light divided by wavelength. Okay, the speed of light, the unit right here. The unit for speed of light is meter over second. So therefore, the wavelength we have to convert from nanometers to meters. So this is the energy for one photon. Then to find out the energy for 1 mole of photons, we need to apply the Avogadro number. In 1 mole, there are 6.022 times 10 to the 23rd photons. So the energy for 1 mole of photon is 239 kilojoules per mole. Let's take a look at the electromagnetic spectrum. This is the frequency axis, higher frequency on the right-hand side. The second one is the energy axis. And the third one is the wavelength. Okay? We already know short wavelength or high frequency has higher energy. So high frequency is this end, and short wavelength is also the right-hand side, this end. Therefore, for the energy axis, on the right-hand side, we can find the highest energy. From this spectrum, we can see radio waves, they have the lowest energy. Of course, they also have the lowest frequency, and they should have the longest wavelength. And then the energy is increased from radio frequency region to microwave, then infrared or IR, then the visible region. Now you understand the visible region comprises only a very small fraction of all wavelengths of light. Okay? Then after that, we have the ultraviolet, UV, X-ray, and gamma ray. Energy is increased from the radio wave region to gamma ray. Okay? And then, of course, gamma rays have the shortest wavelength in this spectrum, and radio waves have the longest wavelength on this spectrum. And now let's zoom in the visible region. Red lights, they have the longest wavelength, and they have the lowest energy or the lowest frequency. And then the blue and the violet lights, they have the shortest wavelength, 400 nanometers. Therefore, their energy is the highest in the visible region. High energy radiation can, of course, potentially damage your skin, all right? That's why when you go to beach or you go to outside to get tan, you need to apply sunblocks, sunscreens, so onto your skin. So now we'll look at the spectrum from another angle. Those are the radiation regions, gamma rays. It has the shortest wavelength and highest frequency in this table. That's why gamma rays has the highest energy, as we just talked about in the previous slide. Then go all the way to radio waves, the lowest energy, the longest wavelength, and the shortest frequency. But here they give you the range of the wavelength and frequencies, okay, in this table. And now let's zoom in to the visible region. Here are the wavelength and frequency ranges for the radiation in the visible region. These are the end of lecture 33 quiz questions, and that's it for lecture 33. I will see you guys in lecture 34.